In this lesson, we're going to be looking at the speed in which the two different sorts work, sequential and binary. So we're going to be using arrays, so we have to import java.util.arrays. Now, sequential search and binary search both require a number of iterations to find a target in the collection. How each search works is quite different, resulting in different speeds. Now, sequential search starts at the beginning of the collection, looking at each element until it finds the target. The collection doesn't need to be sorted for the sequential search to work. Binary search works by continuing to split the array into half. Thus, it's able to only look at a smaller and smaller data sets. So a collection of size 100 is broken down into 50, and then 25, and then 12, 6, 3, 2, 1, because it keeps halving it. But binary search does require a sorted collection to work. Now let's look at what is called big O notation. It's used to clarify algorithms by how fast they're able to work based on an input size. The input size is the collection, the size of the collection. We're going to say it's size n. Now, sequential search, it's classified as O of n. In other words, collection of size n will take O of n speed. So its best case on a sequential search is O of 1. It found it in the first try. But its worst case is O of n, which is the last element, or it's not in the collection. So its worst and its average speed is O of n. Now, binary search, its speed is much, much faster. It's O of log n, which is much quicker. So the larger n is, the faster binary search becomes. So if you have an array of size 10, comparing sequential to binary, they're not, binary search will be faster, but then you go to an array of size 1,000, comparing sequential to binary, binary is just incredibly fast compared to it. So the more elements you have, the faster binary search works in comparison to sequential search. And a binary search, best case, O of 1. It's found in the first try. But its worst case is its average speed, which is O of log n, which is it found it in the last place it possibly could be, or it's not in the collection. So we're going to compare these. So here's our sequential search array that we're going to use. We can notice that it's not sorted. And we'll look for these elements, 7, 25, 0, -2. Our methods, though, return something different this time. They're going to return how many iterations it took to find the target, or potentially how many iterations it take not finding the target. And then we're going to do the same sort of thing with sequential search, except our array is going to be sorted because, in binary search, because remember, on binary search, our array has to be sorted. Now you'll notice that doesn't really impact sequential search speed, because sequential search is not impacted whether it's sorted or unsorted, but binary search only works on sorted elements, sorted arrays. So here's our sequential search. You notice what it's going to return. The length of the array is 0, it returns -1, but otherwise it returns I plus 1, which is the number of iterations. Or it returns the length of the array, which again is the number of iterations if it didn't find it. In binary search, it also returns a number of iterations. So every single time this while loop runs, iterations is increased by 1. And see here it returns the number of iterations. So let's look at our speeds here. So sequential search using an unsorted, you can see that speeds 8, 9, 10, 2, But when it's sorted, it didn't really increase in its speed, 6, 8, 10, 1. It was marginal, but that was just purely because the elements we were looking for. But then look at the speed of the binary searches, 1, 4, 4, 3. In general, much, much faster. And if we used larger and larger array sizes, the efficiency of binary search over sequential search just becomes greater and greater. And so that is the end of this lesson.